Welcome back to ECE 501B. Homework number 3 is due on Monday, and you can't hand that in during class because I won't be here, but watch for the lecture on that Monday via video and notes. Hopefully that will get posted to D2L, and our exam is a week from today. Because we physically won't be meeting between now and the exam. Obviously, I do have office hours, and there is review material. There's actually a video, I believe, for practicing or a review session for the exam number 1 from a previous semester, but it's consistent with what we've been talking about this semester. I want to talk first about the process for exam number 1, and that should be available in the notes section under exam number 1, but I'll just quickly highlight what you might be, what you should maybe be expecting a week from today on exam number 1, and then we'll pick back up with chapter 3 and talk about an important note on this concept of a map and its matrix representation, or a way of representing that map via a matrix representation, so that we don't get hung up on the matrix representation per se. Then we'll talk very quickly about addition and scalar multiplication of matrices, matrix multiplication, matrix vector product. We'll then continue with what does it mean for a map to be invertible. And in that case, we know that it needs to be one-to-one and onto, or injective and surjective. Then we will talk about isomorphic vector spaces, which really means that they are similar in terms of, now given maybe a very abstract vector space, if it's the same dimension as another maybe R5 or an R6, then if those are the same dimension, then those can be shown to be isomorphic. And so what you can sort of think about in R5 can be conceptually thought of in the more maybe abstract vector space. We'll then get into operators, which when we speak of an operator, then the input vector space and the output vector space are the same. It's mapping from that space back into itself, and we'll call that an operator, in addition to it being a linear map. But then we will specialize it to say that also can be referred to as an operator. The process for exam number 1, you can bring in 2 sheets of notes, front and back, and those sheets can be restricted to 8.5 inches by 11 inches. So don't go any larger than that on your sheets, but you now have essentially 4 sides of paper to give yourself whatever you think you need based on what you've had to do on the homework assignments and for the practice exams. You can bring a graphing calculator. I don't think it matters if you bring in a 4-function calculator versus a graphing calculator. I don't think either one will give you an unfair advantage. Maybe the 4-function will give you a better advantage because you won't be trying to find something on your graphing calculator that maybe you shouldn't be looking for in the first place. But a calculator is allowed, something to write with, but that's really it. All the other items are no's. No textbook, no class notes. You do have already 2 sheets of notes. No cell phone, no computers, no classmates, no help. And I should say that because this is online, please do not discuss this outside even after you finish the exam, because some other people might be needing to take the exam after you've already taken it on Wednesday. Okay? So just everybody sort of be mum with the exam, and we should be okay. I just want to make it as fair as possible. The structure, there'll probably be 5 problems, and one of those problems will probably involve a proof. You may have to come up with a show or a demonstration using definitions, propositions, theorems, or you may need to produce a counterexample to show that something doesn't hold or that something's not good. And you may need to be able to create or build with these different concepts that we've been talking about with vector spaces, subspaces, direct sums, basis vectors, matrices, whether you have an injective map, surjective map. Can you start to be creative or building with those ideas or concepts? That's the structure and the process for exam number 1. Questions about that, and you should be able to find some example exams on the website to practice. Question? Are we getting your homework back? I can't promise that. I apologize, and that's one maybe benefit of scanning it and uploading it. At least you should have solutions to look at. Meaning, I think I've tried to upload or provide solutions, but unfortunately I don't know where my grader is at relative to grading the homework problems. So expect those grades to be reported by the end of the semester, but I don't know when I can tell you those will be available to you. I'm sorry for that. Let's then pick up where we left off, and really I just want to make this disclaimer or this extremely important note about maps, and that is the same as vectors can sort of numerically look very different but maybe mean the same thing. Last time we saw, depending on what our underlying basis was, we could see that a vector 1, 1 means the same thing as a vector that's 1, 0. Numerically, it depends on what the basis are that you're using in terms of how to interpret that. But the mapping themselves, those don't really change. So as with vectors, maps have an existence separate from their matrix representation. Choosing different basis changes the values or the scalars in the elements of the matrix, but it doesn't change really what the map is doing. If it's taking something and rotating to another location, then that linear map is doing the same thing, but the matrix representations, depending on how you're representing that with basis vectors, may look completely different. Here are the matrix main operations. Matrix addition is element-wise. That shouldn't come as a surprise to anyone. And if we scale a matrix, that just means every element is scaled by that same scalar amount. But once we have those matrix operations, we can actually create a new vector space. We've learned that we can come up with different vector spaces, and here's another one based on those two matrix operations. Using the above, two operations which go hand in hand with, well, let me just say these conventional, which was matrix addition and scalar multiplication of a matrix. So here I'm trying to say conventional matrix operations of addition and multiplication on matrices, we can define a new vector space, where that new vector space is now going to be these matrices. So let me just call it an M by N matrix, so it can be any generic matrix size over a particular field, F, either the real numbers or complex. This is now our set, and we need a set with those two operations, addition and scalar multiplication, to create a vector space. So matrix, an M by N matrix over a field is the set of all M by N matrices with elements belonging to the field F. And what's the dimension of that particular vector space? So now we have this M by N matrix that now forms a vector space, meaning we can do all the vector space operations with these matrices. And now I'm asking, if we had to sort of say what's the dimension of that vector space, what would it be? Or what's the dimension of this matrix that's M by N over F? Or if you wanted to compare this dimensionally with another vector space, pardon? So this is, we have M by N opportunities. It's essentially like an M by N column vector, because now we're treating this as a vector space. And so essentially you could think of it as concatenating all the rows or concatenating all the columns. It now comes into an M by N dimensional vector space. And it takes, one way of thinking of this is it takes the product M times N numbers to specify. Meaning, what would be maybe a conventional way of finding a basis for these M by N's? Suppose that M was 2 and N was 3. What would be maybe the first standard basis vector? Now these matrices are vectors. And we could say, what is maybe V1? It now has 6 elements. And we want to know what might be considered a standard basis vector in this 3 or 2 by 3 matrix vector space. Typically, our standard vectors are a 1 in one element and zeros everywhere else. What would you speculate might be a convenient first vector in the basis for this? Maybe we have a 1 there and zeros everywhere else. Because now, how big is our vector space dimensionally? 6, right? It's 2 by 3. So now we could look at V2 being 0, 1, 0, 0, 0, 0, etc. And we would have then 6 basis vectors filling in a 1 into each of those individual element locations and zeros everywhere else. And then you can now find you could span the entire space by a linear combination of those basis vectors. And that's now a different way of thinking of a vector. Now a matrix is a vector in this vector space. Let's look now at matrices as being matrices and talk about multiplication. Using the matrix representation, of a linear map. And if we think about what is really happening, if we look at multiplying matrices, that's like starting in some input vector space, and when you map that through a matrix, you go to an output vector space. But for these matrices to be compatible, to multiply them, then that output space of the first matrix needs to be the input space to the second matrix, and then that produces finally the eventual output vector space that we want to end up in. Let me see if I can write that out. In the special case where we have a linear map T, and let's say that's going from an input vector space U to an output vector space V, and we now want to multiply that on the left, let's say by S. What do we need this linear map to be moving between or starting in if it does need to be at all consistent with T's vector spaces? S now needs to start in the output space of T. This now needs to start there, and then where it ends up is depending on what we're trying to do with that linear map. But we have this. S is now operating on the output of T. The multiplication of the maps could be sensibly defined as follows, where we might write the multiplication of these two linear maps, ST, operating on a vector V, is the same as taking the output from TV and mapping that through S. Relative to matrices, though, or multiplication of matrices, what do we, I hope already, are we familiar with in terms of how are S and T related to T and S? They're not necessarily equal, are they? So matrix multiplication does not commute in general. So the product of ST, it may not even be well defined. The matrices may not even be compatible. So you may not be able to change the order in terms of how you perform those. But now we want to know, now we're talking just in terms of general maps, what happens about the matrix representation? How does this multiplication work in terms of matrix representation? I think we can anticipate what we would want. We would like for, if somebody now looked at the matrix of these two linear maps taken one after the other, it would be nice if that was the same as the matrix representation of S applied to the matrix representation of T. And in fact, that's given as one of the propositions in the textbook in Chapter 4. It's proposition 43 in Chapter 3, that indeed this is true. This is what we would want, and in fact, it's what we have. And this multiplication works fine using the standard definition of matrix multiplication. And we'll spare you that. We're not going to go over how to perform the brute force matrix multiplication. If you need to, you can review. But this concept of matrix multiplication from a definition, we're not going to cover. However, I would, if you haven't thought of matrix multiplication in the way that I'm going to present, I would like for you to start being able to think of matrix multiplication in the following way. Another way of thinking about multiplying matrices or matrix multiplication can be helpful in trying to understand or visualize or interpret what's going on when you start to perform multiplication of matrices. Suppose we start with an A matrix. Let's say it's 3 by 3, 1, 6, 4, 5, 2, 5, 7, 1, 3. And maybe we want to multiply, so that's our A matrix. And maybe we want to multiply that by 1, 0, 0, 2, 0, 1, 0 minus 1, 0, 1, 1, 0, and 1, 0, 2. That's now our B matrix. And thinking about it the way that I'm trying to get you to think about it, you should be able to write that down, the result, very quickly by inspection. Meaning the very first column is 1, 5, 7. Then the next one is actually 6, 15, and 17. The next one is minus 6, minus 2, minus 1. The next one is 7, 7, and 8. And the last one is going to be 9, 15, and 13. And how did that happen? I wasn't going row times column to get each individual element. I was now looking at, for example, if I now said, what happens in the third column right here? Well, I can find what that's going to be by concentrating on the third column in B. And the third column in B is really saying, scale the first column with a 0 weight, scale the middle column of A with a weight of minus 1, and scale the third column with a weight of 0. And you should see then that the third column in our product is just the negative of the middle column of A. This is simply saying, oh, I need to take the negative of the second column of A. And that's different from maybe what you might have thought in terms of the traditional. If I wanted the second row first column element, I might have said, oh, that's going to be the second row times the first column. Instead of doing that over and over again, now what I'm suggesting is, oh, in fact, if we just look at this first column of B, how is that weighting the columns in A? If I looked at the result, the C matrix, and I said, oh, the very first column in the C matrix is going to be a result of a particular weighting imposed on the columns of A from the first column of B, what's B's first column doing to the columns in A? It's taking the first column and just copying it, and then adding 0 of the second and the third. So the first column of C better be the first column of A. Is that clear? And then if we said, oh, then the second column of C relative to what B is, I just need to double the first column of A and add the third column to it. And that allows me then to say, oh, I have 2 plus 4, or 6, in my 1, 2 entry in that column. And that's what I'm hoping you can start to envision. And what are we really saying, or what does this now show? This says that wherever we get to in the C matrix is a linear combination of the columns of A. So we are going to end up in what? The range space of A with our matrix. We're going to now be linearly combining these columns in A, and what happens when we say the span of those columns? That's now our range space. And so if there was redundancy in the columns of A, we may not be able to fill up all of the three-dimensional space that is being A is putting us into. If all three columns of A are linearly independent, then we can fill up the entire space depending on how we combine those particular columns with the B matrix. Another way of thinking of this is really sort of just the reverse, and sometimes it's easier. I usually like to be thinking column-wise, but you could also think of the rows of B being weighted by the rows of A. So now, if we wanted the first row of C we would say, oh, I now need to weight the first row of B with 1, the second row with 6, and the next row with 4. And I just have a more difficult time of thinking about scaling the rows, but it's the same concept, and sometimes it might be easier to view matrix multiplication that way. And so you can think about it as either starting with the columns of A or starting with the rows of B, and that then translating into your product C matrix. Meaning we can think of matrix multiplication as combining columns. And which columns are we combining? Those were of A, right? We were trying to linearly combine the columns of A, or you could think of matrix multiplication as combining rows, where the rows that we were combining were the rows of B. Now, if we keep track of the standard way of multiplying matrices, or the standard matrix multiplication, allows us to keep track of when are matrices going to be compatible in terms of performing the multiplication. Which it's now maintaining these properties that we really want. Where if we are given an A matrix that, let's say, lives or is dimensionally living in this matrix that's M by N, where the elements in that matrix are coming from the field of real numbers, and if we have another matrix B that's coming to us that is dimensionally J by L, then when can we define the matrix product? AB is only defined under what relationship between M, N, J, and L? We need N to be the same as J. Or that's really saying that this is equivalent to the requirement that the output space of one map must be the input space of the other map. And we've already talked about matrices maybe not commuting. Even when the multiplications are defined, or when the matrices are even compatible to be looked at as far as one on the left and one on the right, it still may not be the case that the matrix representation of T operating on the matrix representation of S is still not necessarily equal to the matrix representation of S operating on the matrix representation of T. So even if they are compatible, and even if it makes sense to multiply T by S matrix-wise and S by T, even if they're compatible, it may not be equal. We can also work with vectors. Which is given to us in Proposition 52 of Chapter 3. And that says, given a linear operator, or a linear, shouldn't say operator, given a linear map, not yet anyway, where the map is taking us from the input vector space V to the output vector space W, and suppose that we now have basis on V. Let's say that basis is of length n, and basis on W then the matrix representation of TV is the same as the matrix representation of T times the matrix representation of V. So that's dealing with these typical ideas or concepts that you're familiar with in terms of matrix addition, scalar multiplication of matrices, matrix multiplication. Now let's talk about a matrix being invertible. A linear map T that is coming from the set of linear maps between V and W is said to be invertible if there exists a map S. And now, where does this map need to live in terms of input and output vector spaces? If this is going to be the inverse of T, or if it's, so now it depends on where you sort of put this, but now we want to say, you could think of it as, okay, I want it to be S operating on T, then S needs to have W as its input vector space, and V as its output vector space. It needs to return us to where we started. So we need S to live in this linear map from W to V such that ST is the identity map and we might just refer to that as I, and we also need TS to be the identity map. And we can now create a definition. A map S such that ST is equal to I and TS is equal to I is what we will refer to as the inverse of our linear map T. So if we say the inverse of T, then we mean that S needs to satisfy this relation, these two conditions. That ST is I, or is the identity map, and what does that mean? That if I give you a vector V in the input vector space, and you map it through the identity map, where will you end up? Back in the same space that you started at, did I say just V? At V. Or V sub 1, if that's where you started. If the inverse exists, then it is, or it's unique, and we actually give it a special symbol. We don't just keep calling it S necessarily. That might get a little bit confusing. We give it the symbol T inverse. Proposition 56 tells us what a map, a linear map, needs to, or what it needs to look like in order for it to be invertible. And we've already been saying that in our goals, but a linear map is invertible if and only if it is injective, which is 1-to-1, and surjective, which is onto. Instead of looking at the formal proof, I'll refer you to the book, but let's think about this intuitively as far as a linear map. If it's invertible, why is it necessary that it needs to be both injective and surjective? And now we're trying to gain maybe a more intuitive feel for these concepts of injective and surjective relative to a linear map, and why does that mean that it's going to be invertible? So let's examine this proposition 56 intuitively. If I said that we had a map, so let's say that if a linear map T is non-injective, what mental image comes to mind? So now injective, which particular space does an injective map deal with? So now it's worrying about the null space, isn't it? What do we know about the null space of an injective map? So it's trivial, isn't it? The only vector in the input space of an injective map is the zero vector. So now if our map is non-injective, we know that the null space is bigger than just the zero vector. So if T is non-injective, then, and once we have a non-trivial null space, I can start making multiple vectors in my input space go to the same point in the output space. And that's going to be a problem when we try to go back the other direction. That's what I'm trying to say or suggest. If T is non-injective, then multiple vectors in the input vector space V map to the same vector in W. Pictorially, then, we could think of this as, oh, if I have a V1 and maybe it goes to this vector, I'll call it W1, that's now T, the linear map applied to V1, and maybe I now have a V sub 2, how are V1 and V2 related? They're differing by a vector in the null space, right, of T. So now what we want to see, this is the one direction. This is from the input space to the output space. But if T is supposed to be invertible, then we need to get back to where we started once we end up in the output space. But if we start now at W1, where do we go? V1 or V2? Depends on the day it is, or the time, or how we're feeling. We don't know, do we? So this would not allow us to perform the invert or the inversion operation, because we remember that a linear map requires a unique map into a unique vector, and this is not going to allow us to go to a unique vector from W1. W1 is trying to get us to V1 and to V2 if we were trying to go back. So remember, a linear map requires a unique output for a given input. And in this example, since our map T we assumed was non-injective, there's no way the inverse map, let's call it S, that is taking us from W to V can exist. Since that inverse map S, since it, S, would have to map this single vector W1 into multiple vectors in V, and that's not possible, since the mapping for a linear map is supposed to be unique, since it would have to map a single vector in W to multiple vectors in V. So that's a reason why T has to be injective. And now let's see why it needs to be surjective also in order for it to be invertible. If T is non-surjective, and when is a map surjective? Now it's dealing with the R. Now the range, what do we want to know about that linear map, if it's surjective, what do we know about the range of that map relative to the output vector space? If it's surjective, we know that the range of this map, if it was T, here, forget that I'm saying it's non-surjective. Let's say it's surjective for this discussion right now. If T is surjective, we know that the range of T does what relative to our output vector space? It fills the whole thing, doesn't it? We can get to any point in our output, we can get to any vector in our output vector space. Here we're saying, suppose T is non-surjective. Now it says we can't reach all the points in our output vector space. If T is non-surjective, then there are vectors in W well, he came in, he was trying to fill the space. He was trying to, but we're talking non-surjective, so he couldn't come into this space, right? So he couldn't quite get to this space. Anyway, for those of you listening, I apologize, but we had a student that came into the classroom thinking it was time for his class. I applaud him for being anxious, but he was a little frightened when he saw this particular class and me up here trying to lecture. If T is non-surjective, then there are vectors in W which are not produced by T acting on the vectors in our input vector space V, or on the vectors of V. But the inverse map S that's going from W to V, somehow it would have to ignore those vectors that we can't reach. It doesn't know what to do with those vectors, essentially. The linear map S, taking us from W to V, would have to ignore those elements in W. But a map acts on all elements of a space. Let me see if I can sort of sketch this or give this maybe a visual way of thinking about this. Here we are. Here is our input space V. Here is our output space W. If our map is non-surjective, then we are not getting to every point in W. That's what my black cloud is trying to indicate. There are points over here that are not getting touched with the range of T. Which means then that if we looked at S, which is trying to go from all of W, if it tried to operate on that vector in W, it doesn't know what to do. S would have to ignore that. And how would it know to do that? So having a non-surjective map does not allow us to have an inverse of that map. Now let's talk a little bit about some of these earlier corollaries relative to invertibility. where we were saying no map to a lower dimension can be injective, which was corollary 23, then what does that sort of look like if we were looking at the matrix representation of that map T? So it's short and wide, isn't it? It's going to a lower dimension. So our matrix representation of that linear map would look like this. It would be wider than it is tall. We know that it cannot be invertible since it's not injective. And we just learned that if we do have an invertible map, it has to be both injective and surjective. But we also have this other corollary that told us that no map to a higher dimension can be surjective. Which was corollary 24. And now this map, matrix representation of that map, is just the opposite. It's now tall and narrow. Which, what I'm trying to get us to think about now is if we have an invertible map, it can't be short and wide, and it can't be tall and narrow. It has to be a certain type. It now has to be neat, doesn't it? Or square. Maybe we don't think of things being square as being neat, but now we need it to be of the same dimension row-wise as column-wise. So we see that inverses only exist for maps between spaces of equal dimensions. And now you've already answered my question. The question was, what does this mean about its matrix representation? And you've already envisioned what that means. What does this mean in terms of matrix representation? Do I hear a question being formed? So now I think what we need to be careful on, maybe I'm jumping in too early, but we were talking about a map to a lower dimension. And now what that says is, where does our null space live? In what vector space? It lives in V, doesn't it? And what do we know about that vector space? It's non-trivial if we have something that's mapping to a lower dimension. So it's not the map is not injective because we have a non-trivial null space. But then the question, or maybe the statement or the question, the statement was all vectors in V will map into W. So all vectors in V will map into W, but that doesn't mean that you might get some vectors that produce the same output, right? Because now you have non-zero vectors V that give you nothing, that map you to the zero vector in your output space because you have a non-trivial null space. So you have this picture that we were dealing with before. We can start at two different locations in our input vector space and map to the same point, W1. And we don't want that if, in fact, we want a invertible map. Now, just the fact that our matrix representation is squared doesn't guarantee that that linear map is invertible, because we could still have a non-trivial null space, or we could still not have a surjective map, even though our linear map, may be going from one vector space into the same sized vector space. Then our matrix representation would be square, but we're still not guaranteeing that that map is invertible. Just because our matrix representation is square doesn't mean that it's invertible. But it has to be square to even have a chance of being invertible. I don't know if that helps or not, but we need to kind of keep all of these things straight in terms of mapping to a lower dimension and mapping to a higher dimension. That's out of the question if we want to start talking about an invertible map. So if you have such a map, you can immediately say, well, I know that I can't find a linear map that's the inverse of any of those maps that are going to a lower dimension or going to a higher dimension. You can immediately make that conclusion. So now, if we think about this, we have the columns of the matrix representation of T. Remember what we were doing? We were saying, oh, we have TV1. That was forming the first column of our matrix representation of T. TV sub 2, that was our second column, etc. And we went, let's say, down to T operating on the nth basis vector. And those were expressed in terms of, or that they had to be linear combinations of the basis vectors in our output vector space, which we were usually using W's. So this now was expressed as some linear combination of W1, W2, up to W sub n. So the columns of our matrix representation of T, which are TV1, TV2, up to TVN, they had to be linear combinations of our W's. And now what we're seeing then is we need the same dimension of our input vector space and our output vector space, which says that we do have the same dimension only if n and m are the same. Which now says that the number of columns, that was the TV1, TV2 up to TVN, that has to equal the number of rows. That's how we combine these m basis vectors in our output, and that's why we have in our matrix representation a square matrix, or only square matrices have an inverse. So now that we've talked about linear maps having an inverse, we can introduce a new concept, and that concept is isomorphic. Two spaces are said to be isomorphic if there is an invertible linear map between the spaces. So if you give me one vector space and somebody else gives me another vector space, we would like to know, when are those vector spaces isomorphic? They're isomorphic if there is an invertible linear map between the spaces. So if you can find a map between vector space A and vector space B, and if it's invertible, then those two vector spaces are isomorphic. And two isomorphic vector spaces have the same properties. The other thing that we can think about when we talk about spaces being isomorphic, I'm trying to jump ahead to chapter 5, which we're not quite there, but we're up into the 50s with our theorems. Theorem 59, 2 FDVS, finite dimensional vector spaces, are isomorphic if and only if, what can we say about their dimensions? They have to be the same. So if and only if they have the same dimension. So let's look at a proof of that. It's an if and only if, so we need to show it in both directions. First, let's assume V and W are isomorphic. So now we're assuming statement A, and now we want to show that statement B is true, that V and W are the same dimension. So we're assuming V and W are isomorphic finite dimensional vector spaces, and by definition of isomorphic, this in fact means what? There's an invertible map between those. So now by the definition of two vector spaces being isomorphic, this means there is an invertible map and it's linear that exists between V and W. And if we have an invertible map, what properties does that linear map now possess? So now we know that T is both injective and surjective if it's invertible. So invertible implies injective and surjective. And what do we know about injective and surjective relative to maps that, or sort of the dimensions of these maps? We use those corollaries now, in a sense. No linear map is injective to a finite dimensional vector space of blank dimension. So now if we have a map into a lower dimension, our map is not injective, is it? It has a non-trivial null space. So here, no linear map is injective to a finite dimensional vector space of. Now if we're going to a smaller, it's not going to be injective. So that's what this is saying. No linear map is injective if it's going to a smaller dimension. Or now we've shown that the dimension of V, that was our input vector space, is less than the dimension of W if it's not injective. We also can do a similar argument for surjective. No linear map is surjective to a finite dimensional vector space of larger dimension. So here we need the input vector space to be less than or equal to our output vector space if we want our map to be injective. If we want our map to be surjective, we need the dimension of our output space to be less than or equal to the dimension of our input vector space. We don't want our output space to be larger. Now we can combine those. This says then that if we start with the dimension of V, then using the first one, we see that that's less than or equal to the dimension of W, but the dimension of W is less than or equal to the dimension of V. So now we've sandwiched the dimension of our output vector space between the dimension of our input vector space, and that now allows us to say, therefore, the dimension of V is the dimension of W. So now that's sort of the first part, or the first piece of that, and now what do we want to do? Now we want to look at the dimensions being the same and seeing if we can conclude that those two vector spaces are isomorphic. Second step, maybe what I'll do is I'll fill that in after class and just write that down, sort of the steps of this, but now we're into the second part of our proof. We're going from statement B implies statement A. We've just shown that statement A implies statement B. That a map being isomorphic, or that if we have two finite dimensional vector spaces that are isomorphic, then they have the same dimension. And what we want to do now is talk about if two vector spaces have the same dimension, are they isomorphic? and that's where I will fill in after class.